Okay. Okay, thank you, Dr. Nadia, for your kind introduction. Thank you all for your time. I would like to thank IEEE Photonic Society as well for giving me the opportunity to talk about my research work, which is 1.3 micron fiber laser sources development using praseodymium dot fiber and bismuth dot fiber. So before we go further to 1.3 micron fiber laser sources, let's take a look at the introduction of the fiber laser. So in 1931, mass production of glass fibers is conceived. 20 years later, there's first discussion of using transparent cladding on glass and plastic fiber. In 1959, American Optical draws fibers so fine that they can only transmit single mode light. And in 1960, first fiber laser was demonstrated by Schnitzer and his colleagues. 10 years later, first low loss optical fiber for telecommunication system was fabricated. And one of the most important events in fiber laser history is the discovery of erbium dot fiber amplifier by Payne and his colleague. So fiber laser and fiber amplifiers are nearly always based on glass fiber, which are doped with rare earth ions, normally only in the fiber core. So such fibers are often called gain fiber or active fibers. So rare earth ions are good candidate for active ions in laser materials because they show many absorption and fluorescent transition in almost every region of the near infrared range. So for instance, we have emission in 2 micron region with thulium and holmium dot fiber. We also have well-known erbium dot fiber that has emission at 1.5 micron. And we also have ytterbium dot fiber that has emission at 1 micron. So why fiber lasers? Fiber lasers provide simple operation with alignment-free, easy integration, greater stability, and low maintenance costs. So due to the wide range of possible power outputs, fiber lasers are effectively used in many different applications. Some of these are optical communications, material processing, in medical, and also in optical spectroscopy. So emission at 1.3 micron can be obtained with rare earth ion, such as praseodymium. Okay, nevertheless, this emission is absent in silica holes due to the high phonon energy, which is around 1100 per centimeter. So in this case, fluoride fiber has attracted substantial attention due to their low phonon energy, which is only around 600 per centimeter. So Zeblan glasses make particularly good host material for active laser devices, such as fiber lasers. Zeblan is the most stable composition of fluoride glass. It has low phonon energy, high allowable rare earth ions doping level, which is around 10%. It exhibits a broad transmission range from 0.2 to 8 micron. However, it has low mechanical stability, so it needs special coating to protect the fiber. A brief history of rare earth doped Zeblan fiber. The first lasing in fluoride glass host was reported in 1987. They managed to get lasing at 1050 nanometer from neodymium multimode fluoride fiber. And a year later, 1.34 micron lasing is observed from neodymium Zeblan fiber laser. And in 1995, a 3.9 micron emission is obtained from holmium doped Zeblan fiber laser. So basically, this discovery has spurred the development of rare earth doped Zeblan fiber for laser generation at wavelength regions which are absent in silica host. So this is the list of rare earth ions. with their respective emissions in Z-band. For example, we don't have 3.9 micron in silica, right? So this is a kind of unique emission that we can obtain in Z-band host. So the figure shows various emission wavelength of rare earth doped Z-band fiber in the visible, in the near infrared, and mid-infrared region. Also marked here is the major emission wavelength which enabled by rare earth doped silica. So this is the ytterbium doped silica, erbium doped silica, and also the well-known thulium or holmium doped silica fiber that has emission at 2 micron. So in praseodymium doped Z-band fiber laser, so this is the energy diagram of praseodymium doped Z-band fiber. By pumping at 1020 nanometer, the PR3 plus ion at the ground state can be excited to 1G4 excited state, which happen to be its metastable state as well. A radiative transition occurs from 1G4 to 3H4 to 3H5, induced by a signal photon with equal energy, and this process we call as stimulated emission. It is crucial to know that the lifetime of this metastable state can be greatly reduced by the non-radiative decay process, which involve a simultaneous emission of phonons. This process, we call it as a multi-phonon relaxation. Okay, the efficiency of this radiative transition depends of the lifetime of the metastable state here. And it is important to know that the lifetime of this metastable state can be greatly reduced through the multi-phonon relaxation from 1G4 state to 3F4 state. This is the simplified energy diagram of praseodymium and the energy transition in silica and also in Z-band, in fluoride. Unfortunately, when doped in silica fiber, emission from PR3 ion is very poor due to its large phonon energy. Okay, remember it has 1100 per centimeter phonon energy. In silica glass, the praseodymium ion that excited to 1G4 metastable state rapidly decays to 3F4 by generating multi-phonon relaxation, through multi-phonon relaxation. So, while in fluoride, a large number of phonons are required for such radiative decay because the fluoride phonon energy is relatively low compared to silica, which is around 600 per centimeter. So the probability of the decay decrease with the required number of phonons. And thus, no radiative decay is not happening here. It's well suppressed. And efficient emission can be obtained using emission efficient at 1.3 micron can be obtained by using Z-band. Okay, since we are talking about fiber laser sources development, let's move on to the technique of generating pulse laser source. There are two types of pulse laser, namely Q-switch and Mortlock. So Q-switching technique is mainly applied for the generation of nanosecond pulses of high energy, whereas Mortlock technique generates ultra-short or ultra-fast pulses with high peak power. So this pulse laser can be generated through passive and active means. In this lecture series, we are going to discuss the passive technique utilizing saturable absorber for Q-switching laser, Q-switch laser, and also Mortlock laser. So, saturable absorber is a material or device that has a low absorption at high intensity light. So, absorption decreases with intensity and become transparent at high intensity. Light with low intensity will have much of its photon absorbed by the electron to be excited up to the conduction band of the saturable absorber. So, in the case of high intensity light, the absorbance of the photons reduces due to the occupation of the electrons in the conduction band, which are excited by the photons from the low intensity light earlier. So this is according to Pauli's blocking principle. The development of saturable absorber ranged from CSAM to low dimensional material. For example, we have zero dimensional material, for instance, quantum dots. We have 1D material, for example, nanotubes, nanowires, nanorods, and we also have 2D materials, for example, graphene, topological insulators, transition metal D-chalcogenide, black phosphorus, and also enzymes. 2D materials are one of the most vigorously investigated materials in modern science. So there are various advantages of using 2D materials as saturable absorber. For example, it has 2D material provides strong nonlinear SA properties. It has broadband applied wavelength range, dependent optoelectronics properties, H threshold. So next, we move to the pulse laser generation in PR3+ Zeblan fiber. So the PR3+ Zeblan fiber used in this work is purchased from Fiber Labs Incorporation. It is 11.7 meter long with PR3+ concentration of 2,250 part per million. It is hygroscopic. So this enclosure module will keep the fluoride fiber from humidity. And the cavity setup of the pulse fiber laser in this work consists of palm laser at 10 we have our gain medium and optical coupler. So we managed to observe Q-switch pulses in PR3+ Zeblan fiber using graphene. So the Q-switching operation is observed operating at center wavelength of 1301 nanometer with frequency of 30 kilohertz and the minimum power of 3.5 microsecond. So the power dependent repetition rate and pulse width of the Q-switch pulses can be clearly observed, as you can see from this graph. As we increase the pump power, the pulse repetition rate increase and the pulse width decrease. This is due to the nonlinear dynamic of the gain medium and the saturable absorber itself. The output power of the laser is recorded around 26 microwatt. Which pulses were observed in PR3+ Zeblan fiber using TND as saturable absorber. So this has been published in IEEE Journal of Quantum Electronics. The features of the Q-switch and the performance are more or less the same as previous Q-switch. Same goes to the output power. It is recorded around 24 microwatt, because previously we got 25 microwatt. And next is the generation of mod lock. Previously we discussed Q-switch, and now is the generation of mod lock, because the mod lock laser operated in the Q-switch. The mod lock pulse operated in the stretch pulse regime. So that explains the smooth and broad spectrum without any spectral sideband, or that Kelly sideband of the soliton. Which are typical of stretch pulse laser, GVD of PR3+ Zeblan and negative GVD of SMF28 allows periodic stretching and compression of the intracavity pulses. So that's why we observe the stretch pulse laser in this fiber laser. The laser has frequency of 5.9 megahertz with pulse wave of 1.13 picosecond. And the maximum output power of this 1 milliwatt is quite high for mod lock laser compared to the Q-switch laser. And the stability of the mod locking operation is also evaluated by monitoring the optical spectrum of the laser emission for 1 hour. The power fluctuations or wavelength are observed. Next is the development of multi-wavelength lasers in PRT plus Z-blunt fiber using stimulated Brillouin scattering effect. So the schematic diagram of the multi-wavelength Brillouin is depicted here. BP is injected to the laser resonator, the direction through the 50% port of 3 dB coupler. So when the BP pump reaches the Brillouin gain medium, so in this setup, we used 2 km SMF as the Brillouin gain medium. The first order Brillouin-Stokes line, which is the BS1, is generated on the condition that the BP exceeds the threshold, the Brillouin threshold of the BGM. So the generated BS1 propagates in a counterclockwise and is amplified by this gain medium, after which it continues to propagate until it reaches another end of the Brillouin gain medium. At this point, if the BS1 exceeds the Brillouin threshold of this BGM, the second Brillouin-Stokes will be generated in the same direction of the Brillouin pump, or meaning to say it is always opposite from the seat, which is BS1. For the generation of BS2, it is dependent on the BS1, right? So if the BS1 propagate in the counterclockwise, the generation of the BS2 will be the other direction, the opposite one, which is the clockwise direction. So this process repeats itself until you get the multi-wavelength spectrum over here. So due to the nature of the cavity, only even orders Stokes line are observed at the 5% output. So you can only see Brillouin pump, Brillouin-Stokes 2, and if this process repeat, you can also see BS4, BS6, as can be seen here, until 36 Stokes. Whereas the odd order, the BS1, BS3 Stokes are significantly suppressed. And this gives, the double Brillouin frequency spacing in the multi-wavelength fiber laser. The stability of this double Brillouin frequency laser is also investigated. The minimum fluctuation of less than 1 dB is recorded, and the maximum fluctuation is recorded around 1.2 dB. Another interesting work that we did was introducing a 15 micron micro air gap in the laser cavity to switch the operation from double spacing to single spacing. So basically, this micro air gap is formed by maintaining an air gap between two fiber ends, which are aligned coaxially with the help of Fettel fusion splicer. So the Fresnel reflection induced by the micro air gap causes a fraction of circulating signal in the laser resonator to reflect off its initial path. So this results in bidirectional signals that oscillate constructively in the laser resonator. So that's why the switchable of the brilliant spacing from double, the blue one, to single can be obtained immediately upon the introduction of this micro air gap. In this work, the Fresnel reflection is estimated around 3.6%. So this is the performance of this incorporate the 50 micron air gaps. It shows a 21 Stokes lines and 10 anti-Stokes line. So the wavelength spacing is this is a single spacing. So it should exhibit a spacing of 0.07 nanometer. And the stability of single spacing multi-wavelength is also investigated. The minimum fluctuation is recorded around 0.4 dB and the maximum fluctuation is around 1.9 dB. So this work has been published in Optics and Laser Technology. So after working with PR3 plus Zibla fiber for quite some time, we noticed that this fiber has few drawbacks, such as the splicing of fluoride fiber and silica fiber is not straightforward. You need to have a special, or you need to have specific technology to splice these two types of fibers. It has intricate fabrication. It is hygroscopic, fragile, and has limited chemical stability. So that's why it needs to be kept in a special module to protect the fiber from humidity. We also noticed that the output power of this laser is very low, which might be due to the excited state absorption and ground state absorption at signal wavelength 1.3 micron, because 1.3 micron is the desired output that we want. But unfortunately, there might be an absorption at this signal wavelength, thus reducing the laser efficiency. So we know that doping of the core zone with rare earth material is necessary for fiber laser. Various rare earth elements have been utilized, and their emission in a silica host is depicted here. It is visible here that the emission in 1.3 micron can be realized with bismuth dot fiber. So the first bismuth dot fiber was reported by Dianov in 2005. And the bandwidth and intensity of emission produced from bismuth dot fibers are influenced mainly by the host type and other co-doping materials. So basically, they are sensitive to the composition of glass. For instance, bismuth dot aluminosilicate fiber shows a luminescent peak at 1150 nanometer, whereas bismuth phosphosilicate and bismuth doped German silicate fiber (BJSF) with low doping of germanium oxide to a longer wavelength side of about 1.3 micron and 1.45 micron. So by using high germanium oxide concentration within the fiber core, the bismuth emission window is extending to covered wavelength band of 1.6 to 1.8. So basically, it depends on your desired output wavelength. So you can choose different hosts accordingly. We managed to demonstrate a 1.3 micron Pacific switch bismuth dot fiber laser using MZIN central absorber. The key switch output and the performance is more or less the same as the one that we got using praseodymium. The operating key switching laser, the operating wavelength of the key switching laser is around 1.3 micron, and the minimum pulse width recorded is around 7. The measured output in the praseodymium laser, which is around 0.7 milliwatt. So because previously with praseodymium fiber, we got an average output power in the range of microwatt. But in this bismuth fiber, we can get the output power. I would say it is an improvement. Next, we also managed to demonstrate a multi-wavelength generation in bismuth fiber using 2-mode fiber filter. The TMF, the 2-mode fiber filter, has the advantage of a simple fabrication technique, which can be carried out using a commercially available fusion splicer. So you can splice the TMF to SMF. So this filter offers a stable operation, which leads to an economical and non-complex device. So basically, the 2-mode fiber filter was fabricated by splicing the 2 single-mode fiber .
Okay, I think Dr. Bella's internet is breaking up, so let's wait for her for a bit. For the time being, I would appreciate if everyone can register their attendance in the link given in the chat box while we wait for Dr. Bella. And if you have any questions regarding what she has presented so far, you may type them in the chat box as well.
Sister, could you please resend the registration link?
Okay, just did in the chat box. Did you get it?
Yes, thank you.
Okay. Okay, Dr. Bella is coming back. Please stay tuned. Okay, she's here. I will let her share. Okay.
Okay, so sorry for the interruption. I didn't notice. I almost finished my slide, actually. Okay, it's okay. I'll try to share my screen again.
Oh yes, this one. Yep. This was when your internet decided to forgo you.
Here, is it?
Kat sini.
So this one,
Tak.
this
Belum.
one okay. This one belum.
This one belum.
So this is the last slide, is it?
Boleh ulang balik lah lepas daripada yang ni.
Oh, okay. So, okay.
And yang ni dah, the next slide.
All right. Okay. We managed to demonstrate 1.3 micron passive leaky switch bismuth dot fiber using enzine tetraber absorber and B2C. So the key switch characteristics output and the performance are more or less the same as previous key switch, but this time we managed to record higher output power with bismuth. It was recorded at around 0.7 milliwatt. Previously with praseodymium, we only got an average output power in the range of microwatt. So this is quite an improvement for generation of switch in 1.3 micron. We also managed to demonstrate a multi-wavelength generation in bismuth dot fiber using 2-mode fiber filter. The TMF fiber has the advantage of simple fabrication technique, which can be carried out using commercially available fusion splicer to splice the SMF and the TMF. So the TMF was fabricated by splicing 2 single-mode fibers at both ends of 2.5 meter 2-mode fiber. Okay, we have single mode here and a 2-mode fiber here. So basically, when the light launch into the first SMF, the fundamental mode that propagates through the SMF will couple into the TMF, into the 2-mode fiber, which excite higher order mode, which is LP11. And when the light passes through this TMF, they will couple back to SMF, and this is where the interference happen when because of the changes in the relative phase of LP01 and LP11 when they travel in the TMF. So leads to the generation of a periodic foam spectrum here. So the FSR, the free spectral range, is recorded around 0.69 nanometer, and the extinction ratio is around 8.6 dB. It can be seen that all peaks overlap with the peaks of the TMF transmission spectrum. This signifies the lasing occurred from the related peaks of the TMF interference spectrum. So the FWM effect is also studied by comparing the multi-wavelength spectrum with and without SMF. So it can be seen here that high number of peak can be seen with the 2 kilometer SMF compared to the spectrum without the incorporation of SMF. Currently, we are still working on developing other laser sources in 1.3 micron using bismuth. We also improve our laser in praseodymium dot fiber. So a lot of projects that are currently in progress. So, okay, that's all from me. Thank you.
Wow, that's a lot of work that you've done. This is all conducted during your PhD time?
Yes, and also during my postdoctoral.
Oh, postdoctoral.
Uh-uh.
Where did you have your postdoc?
In UM as well.
Yeah, as well. Okay.
Uh-uh.
Okay. Do we have any questions from the audience? Maybe Dr. Bella boleh stop sharing first, so
Oh,
that
okay, sure.
nanti when we have questions, you can go back to your slides, so that we can see your face actually. Okay. So no questions from the audience. So everyone is not excited as I am. Okay. So I have a question. So you said that you needed a certain technology to splice the silica and also the PR3 Z-blend fiber. What was
Okay,
the
yes.
technology that
Fluoride. Actually, it's a fluoride fiber, Z-blend fiber.
So what was the technology that
So
you
basically, we don't have that technology in Malaysia. As I said before, we purchased the praseodymium.zebra fiber, but we actually contacted them to ask about how they splice it. If I'm not mistaken, they have this, it can be either butt coupling or also or mechanical splicing, because you cannot fusion splice these two different kinds of fibers. The fiber itself, like fluoride fiber, has different melting points, right? You cannot fuse, like normally we will use normal fusion splicer to splice two silica fibers, but this one you can either use butt coupling or mechanical splicing. But the technology is kind of they keep it confidential. They keep it confidential.
Okay.
The company itself. So when we bought the module, it has already connected to SMF, so we can just use it with our conventional SMF here.
Okay, understood. We have a question from the audience, from Dr. Amelia Mansour. Can I know where do you get the biphospholicate fiber? Thank you.
Okay, for this is my project when I did my postdoctoral, and this is actually from our collaborator from Southampton University. So they fabricate the fiber and give it to us for us to test and to generate laser sources in 1.3 micron.
Okay. So we have another question from the audience. Dr. Nabila, what are the advantages of 1,300 nanometer region over other regions such as ytterbium, thulium, etc.?
Okay. Why we need 1.3 micron laser, right? So actually, fiber communication has been a game changer in the field of telecommunication. So I think it is projected that more than 60% of the world's population to be connected with internet in 2025, by 2025. So our current fiber communication band is limited to C and L band. Okay, C and L band. So many researchers have proposed various approaches, and one of it is the exploration of 1.3 micron. Because 1.3 micron, it has low loss in silica silica fiber. So that's why we need to explore to 1.3 micron region.
All right. Any other questions from the audience? No questions? Okay. Oh, I do. Okay, Najwa, go ahead. You can unmute yourself if you want. Dr. Najwa? Okay, is it safe if we are exposed to the light in 1.3 micrometer?
Is it safe or not? As far as I know, the safest region that can be exposed to, I assume you are talking about like
I
to
see.
our eyes, maybe. right? So as far that I know is eyes or skin. Okay, so the safest wavelength region that can be exposed to our eyes is 2 micron region, because it is eye safe region wavelength. But in 1.3 micron, I don't think I wouldn't point the laser into my eyes, but because I never read any paper about the safety, the safety of this laser to our eyes. But for skin, it depends on your application, because sometimes you need this kind of laser to do the tattoo removal. Okay, so if you say you want to remove the tattoo remover, if you want to move the tattoo and it needs the ink particles need this kind of laser, so it should be useful to your skin as well.
Okay, so we have another one from Rizwan. Which is better, diode or fiber laser for 1.3 micrometer optical communication?
Which is better, diode or fiber laser? Because right now, fiber communication is a game changer in telecommunication. Silica fiber can be used in various places, under the sea and everything. So I would say fiber laser in 1.3 micron is much better than diode laser in communication. And in addition to the low loss of 1.3 micron in silica fiber.
Okay, so thank you, Dr. Bella. We have another question from Dr. Lim Benzer. In your work, what is the maximum gain measure from bismuth dope fiber and at what pump power?
If I'm not mistaken, okay, can you see my slide, or I haven't shared it?
Not shared yet.
Okay. So I couldn't remember exactly the gain, but based on the laser multi-wavelength laser generation here. Oh, sorry. Based on this wavelength laser generation here, pump combiner to pump our bismuth dot fiber. And the maximum pump power that we use here is around 1 watt. The total maximum pump power is 1 watt. And then we pump it through 60 meter BDF. And the output power of the multi-wavelength laser generation here is only around 0.5 milliwatt. So I would say the gain is not that high for this length, for 60 meter long BDF.
Okay, thank you. We have another question from Dr. Chu, MMU, I believe. Transmission of 1.55 micrometer light in silica fiber has lower losses compared to 1.33 micrometer. So why not making fiber laser at 1.55? So that was the question from Dr. Chu.
Transmission of 1.5 has lower loss compared to fiber laser. Oh, actually we have already a 1.5 matured technology of 1.5 micron fiber laser, but we are exploring other because our communication network is already reaching the limit of communication network or band. So that's why we are exploring this one. This is the second choice of
communication band, right?
Yes, this is the second choice, and it has low loss in silica fiber. That's why.
Okay. Any other questions? Those are really, we have a lot of questions compared to like usual talks. Your talk is famous. Okay, so can you explain more on the two-mode fiber? Where did you obtain this fiber?
Okay, this two-mode fiber is actually a commercial one.
Oh, okay.
We bought it on shelf, and then we just splice it with SMF core, with SMF to fabricate the two-mode fiber filter.
So no other questions from the audience? So no one wants to unmute. Everyone is like typing, just like the students in class. Okay. So thank you so much, Dr. Bella. I really enjoyed your work. Actually, this is like a full exploration on the two fibers, right? So thank you so
Yes,
much
two
for
fibers.
sharing. So I believe no one wants to ask any more questions. They have understood your work very well.
So if you guys have any questions or you are interested in these topics, or maybe you want to further your study in this fiber laser, you can contact me. I can, because I have a lot of friends that are doing a different, sorry?
You can share your email.
Oh, okay. I think I have it on my last slide. So you can contact me, or if you want to do postdoc as well, you can come to our research center. So we have a lot of collaborators, almost complete facilities. So I think you will not regret it.
Okay, Dr. Bella, before we end our session, can we have like a group photo?
Oh, sure.
Okay. Okay. So I want everyone, please, I am requesting everyone to turn on their cameras if you can. I'm sounding very authoritative, like I'm in class. Sorry. Okay. Let me try to make this.
I saw some familiar faces here.
Okay, how do I do this? View, gallery. Okay. So what about everyone else? Can you turn on your video? Dr. Shanan, tak nak on ke? My? Okay. So on the count of 3, 1, 2, give me your best smile. 1, 2, 3. And another slide. 1, 2, smile. Okay, thank you so much. Have a great day, the rest of you, and we'll see in our next talk. Bye. Take care, everyone.
Thank you. Take care.
Thank you so much, Dr. Bella. I really enjoyed the talk.
Thank you, Dr.
Excited. Okay, I'm going to stop recording and turn off the Zoom. Okay.
All right. Assalamualaikum. Bye.
Bye bye.